Unlocking superconductivity's secret, the mysterious halo phase explained. Superconductivity has long been considered a fragile phenomenon, easily disrupted by magnetic fields. But what if it could actually thrive or reappear under conditions once thought impossible? That's exactly what recent groundbreaking research is revealing, and it challenges many conventional notions about how these materials behave. And this is the part most people miss. There exists a rare, high-field superconducting state that forms a sort of luminous halo around certain crystals, giving scientists new insights into the complex dance between magnetism and superconductivity. A team led by physics expert Andriy Nevidomskyy from Rice University has recently mapped and explained this mysterious phase in uranium ditelluride, UTE2, a material that defies traditional expectations. Usually, applying a magnetic field to a superconductor weakens or completely destroys its superconducting state. Think of magnetic forces as the villain trying to break the magic. But in UTE2, things are surprisingly different. Back in 2019, scientists discovered that UTE2 remains superconductive even under magnetic fields hundreds of times stronger than those that typically quench superconductivity. They found that superconductivity seems to vanish at around 10 Tesla, which is already an incredible strength, but then astonishingly reappears at field intensities over 40 Tesla. This phenomenon has earned the nickname the Lazarus phase, playing on the biblical story of resurrection, an apt metaphor for a state thought to be lost but then revived. What makes this even more intriguing is how sensitive this high-field superconducting state is to the orientation of the magnetic field relative to the crystal structure. Collaborating with experimental groups at the University of Maryland and the National Institute of Standards and Technology, NIST, Nevidomskyy's team mapped how this phase depends on the angle of the magnetic field, revealing that it forms a donut-shaped or toroidal halo surrounding a specific crystal axis. Sylvia Lewin from NIST described their findings as both surprising and beautiful, emphasizing how the three-dimensional superconducting halo encircles the crystal's hard B axis, giving a visual sense of how complex and elegant quantum states can be. To interpret these unexpected results, Nevidomskyy developed a theoretical model that could explain the data without resorting to overly complex or controversial microscopic mechanisms. His approach used an effective phenomenological framework. Think of it as a simplified yet powerful lens that captured the essential features of the phenomenon. The model accounted for how the orientation of the magnetic field influences the superconducting behavior, particularly the shape and extent of the halo. A key insight from this work is that the electrons forming Cooper pairs, the fundamental units of superconductivity, appear to carry an intrinsic angular momentum, much like a spinning top. This magnetic spin interacts with the external magnetic field, creating a directional dependence that explains the halo's shape and behavior. Such findings open new pathways to understanding how magnetic fields and crystal anisotropy, the property of having direction-dependent characteristics, interact in these exotic materials. Moreover, the team observed a phenomenon called a metamagnetic transition, a sudden increase in the magnetization of the sample, as the magnetic field strength reaches a certain threshold. Remarkably, the reemergence of superconductivity only occurs once this transition has taken place, and that threshold is highly sensitive to the field's angle. Scientists are actively debating the exact origin of this transition and its link to superconductivity, and Nevidomskyy hopes their theoretical work can help clarify this ongoing mystery. While the exact mechanism, sometimes called the pairing glue, that binds electrons into these unconventional pairs remains elusive, the revelation that these pairs possess an intrinsic magnetic moment is a significant step. It challenges previous assumptions and could lead to new understandings of how superconductivity can be controlled and harnessed in highly anisotropic, magnetically influenced materials. So the next time you hear about superconductivity being easily broken by magnetic fields, remember that nature often has surprises up its sleeve. What other unconventional states might be hiding in plain sight, waiting to revolutionize our understanding of quantum materials? And more provocatively, Could these findings hint at future technologies that leverage these extraordinary magnetic superconducting interactions? Share your thoughts and theories. This is a frontier where debate can be as exciting as discovery.